Hello viewers, welcome to the course on matrix computation and its application. So, this is the first lecture of this course. So, the outline of this course as follows. So, in this course we are going to cover, we start with the introduction to vector spaces, and then we will discuss about the subspaces, the basis and the dimension of the vector spaces. So, this is a introduction to basically linear algebra, and then we will discuss about the linear transformations that are involved in the vector spaces, and we will also discuss a very important theorem, that is rank nullity theorem and its applications. After that, because this course is, as the name is matrix computation, so we will discuss that how the linear transformations leads to the matrix representation. And then after this we are going to discuss with the change of basis and inner product spaces, because in this course we are going to change, we will get the different type of methods in which we will discuss that how we can transform the different type of matrices into the simpler form of matrices. So, that is comes under the change of basis, and also we will discuss the inner product spaces, and after that we will start with introduction to vector and matrix norm, that how we can find out the difference or how we can measure the magnitude of a matrix. Then we will also start with sensitivity analysis and condition number of the matrix, and then we will discuss the special type of matrices, that is called the banded system and positive definite system. We will also going to cover the convergence analysis of iterative methods, for example Gauss, Jacobi, Gauss-Seidel, because in this case we need that how we can find out the matrix norms that will be used in this one. And then we will discuss the Gram-Schmidt orthonormal processes, QR factorization and Householder transformation. So, these transformations are very much important for us whenever we have data and then data is involved with the matrices. So, this type of things are very essential in dealing with this one. And then we will also discuss the very important point, that is called the singular value decompositions, because when in this case we are going to discuss the general eigenvalues, because when the matrix is not a square matrix, then how we can find out the eigenvalues of that matrix. So, that will be discussed by the singular value decomposition, and then we also going to discuss the Morey-Penrose inverse or pseudo inverse, because when the matrix is not a square matrix, then how we are going to take the inverse of that matrix. So, that we are going to discuss with the Morey-Penrose inverse. So, in this course, so let us start with the basics, and the first part of this course deals with the linear algebra. So, in the linear algebra we start with the very basic relation, that is called the binary operations. So, binary operation means, binary means it is discussing the two things. So, this is the definition of the binary operation, that given a non-empty set A, any function from A cross A, because suppose I have some set A, suppose I take a set, it may be a 1, 2, 3, 4, 5, and suppose it goes up to 10, then any function from A cross A. So, this is the Cartesian form. So, Cartesian forms gives you that 1 1 is involved there, 1 2 1 3 up to 1 10, and then I can have 2 1 2 2 like this one. So, A cross A is a Cartesian product in which we going to have a one element from A and another element also from the A. So, this is the Cartesian product. So, binary operation is that given a non-empty set A, any function from A cross A to A is called a binary operation on A and represented by star. So, we are going to discuss that we take a cross A and that goes to A. So, in this case we are applying some operations here, like I take 1 plus 1. So, this is going to be 2 and 2 is also in the A. So, I can say that I have defined this binary operation as a plus sign. So, in this way we can find out, we can apply or we can define the binary operations. Then, so after we apply or we define a binary operation, then we will say that let I take a, so now suppose this is my some set A and I take a subset, so some subset is there, so that is a subset B. So, I will take that B is subset of A. So, let B is a subset of A and then let star be a binary operation on A. So, binary operation on A, it is well defined here on A. Now, if for each pair of elements x, y in B, so now I take two elements x and y that belongs to B. So, I just choose two elements, one is here maybe or one is another here, x and y, and then if I take apply the same binary operation x star y and that also belongs to B, we say that the B is closed under that binary operation star. And if there exists x and y in B such that the x star V does not belongs to the B, then we say that B is not closed under that operation star. So, this way we can define that whether that binary operation, that the set is closed under that binary operation or not. So, that we can discuss. Now, we will define that a binary operation, so binary operation we represent by star on a set A is said to be commutative if A star B is equal to B star A for all the elements A B belongs to the set A. And another property is that associativity. So, we will call it the binary operation star is said to be associative if we take A star and I take the other elements B star C in the bracket, that is equal to A star B and then we take the bracket star C. It means that A star B star C we can put the bracket anywhere among them. So, and if this is true for all value of A, B, C, then we can write this one as A star B star C. So, if this is satisfied, then I will say that the binary operation in this case is associative. So, in this case I will start with the example that how we can define. So, let us take the example. So, how we can say that? So, let I take A is the set where x is an odd integer. So, I take the set A is the set of all the odd integers. Then I define the star, the binary operation as addition. So, in this case I know that if I put x star x, that will be x plus x, and this is the odd integer I am taking. So, I know that the odd plus odd is a even. So, this is a even number in this case, because I know that the 3 plus 3 is 6, 3 plus 9 is 12. So, all are even numbers. So, in this case I can say that, and this does not belongs to A. So, from here I can say that this binary operation star is not closed or I can say that this is not well defined on the set A, or I can say that A is not closed under addition, because only then we will say that it is closed under addition when I apply the binary operation that belongs to that set. Only then we will say that B is closed under that one. So, in this case I will say that it is not closed under addition. Now, for example, now if I choose, so this is the first star I have taken, maybe I can take another star. So, let us take, now let us take this binary operation is equal to multiplication. So, let us take this one. So, in this case I will take that, suppose I take x and star y, suppose I just take y. In this case I taken x star x, I can also take x star y, that is also x plus y. So, that is also even number. So, x star y I am taking as x y. Now, x is odd and y is odd. So, I know that I just taking a simple multiplication and odd integer into an odd integer, that is again a odd integer, because I know that odd into odd in this case, because you can say that 3 into 3 9, 1 into 3 is 3. So, odd multiplied by odd is going to be an odd integer. So, in this case I can say that this belongs to A. So, from here I can say that A is closed under multiplication. So, this is closed under multiplication. So, for the same set I can define different type of binary operations, and for some binary operation I can say that this is closed, and some binary operation it is not closed. So, let us take another binary operation. Suppose I take a set of natural numbers, and in this case suppose I take the binary operation star as addition. So, in this case I know that if x star y, that is x plus y, and adding two natural number is again the natural number. So, that is going to be n. So, it is closed under addition, and also I can have x star y is equal to x plus y, and this can be written as y plus x, because sum of two natural number I can just interchange the position. So, it is y plus x, and this can be written as y star x. So, from here I can say that this is true for all elements x and y belongs to n. So, in this case I can say that this binary operation is a commutative operation on this one. So, it is a commutative, and also in this case if I take three natural number x star y star z, so this one I can apply like this one. So, what I am going to do is, now I will choose this one. So, it is going to be x plus y star z, and that is going to be x plus y plus z, and I can have x star y star z. So, this is also going to be x star y plus z, and this is x plus y plus z, and in this case it is true for all x, y, z that belongs to the set natural number. So, from here I can say that this is true, and it is immaterial where I put this bracket. So, in this case I can say that this binary operation, so this set is associative, is also associative. Okay, so the binary operation, the set is said to be associative if this is associative. So, it is associative in the case of natural number, and the binary operation we are taking is addition. So, in this case it is commutative as well as associative. Now, we can also change the star with the addition with the subtraction. So, you will see that in this case it is even not a closed under subtraction. So, the set of natural number. So, this way we can define the binary operations, and then we can check whether it is closed or not, and commutative or associative or not. So, after this one, the binary operation, we can discuss some algebraic structures that are very important to define the vector spaces. So, first one is I am going to define the groups. So, let G be a non-empty set. So, suppose I take some non-empty set is there, it is my G. So, it is a non-empty set on which a binary operation star is defined. So, star is defined means when I take the two element x and y belongs to G, x star y also belongs to G. So, that is called the defined. So, that is already there. Then G is said to be a group under the operation star if the following axioms are satisfied. So, these axioms are satisfied. The first one is that the star is associative. Associative means if I take the element x star y star z and I put the bracket here, then it should be equal to, and that should be true for all x, y, z belongs to G. So, this is my G, what I am defining. So, it should be associative. Then there exists an element E belongs to G such that E star A is equal to A, and that is also equal to A star E, and this is true for all element A belongs to G, and in this case my E is called an identity element. Okay. So, this is we are going to define for any element. For example, so this is called the identity element, and I can call this identity element as, okay, so we will discuss this one when we will take the example. So, this you just keep in mind that E star A is going to give you A again. So, definitely it is going to be E is going to be identity, because whenever you are applying this on some element, you are getting the same element. So, that is why it is called the identity element. This E is called the identity element. Then the third one is that for each A belongs to G, you choose any element, and if there exists a x belongs to G such that A star x or x star A, that is going to be E. So, in this case what we are going to say, then I can say that x is said to be an inverse of A for the operation star. So, in this case I am going to get the same E whatever we have going to define here, the same E I am getting here whenever I apply the binary operations A star x. So, I am going to get the same value of E. So, in this case I will say that X is said to be an inverse of the element A. Now, so after that, in addition, if I take that if the operation star is commutative, then the group is said to be commutative or abelian group. So, if it is a commutative, as we already know, then if like A star B is equal to B star A for all A and B belongs to G, then in that case I will say that this group is a commutative group or also called the abelian group. Okay. So, note that in the group G, the identity element what we have defined is always unique, and also the inverse is unique for an element in G. So, it is also you have to keep in mind that element E is unique. So, everything depends upon that which type of elements or which type of binary operation we are going to define. Let us take some examples about the group. So, in the group I just start with the first example. I take the set of natural numbers. And in this case I will define that star as addition. Okay. So, in this case let us see that whether it is going to be a group or not. So, I am defining the star as addition. So, addition means this one. Now, I know that first part that if I choose any x plus y, then natural number plus natural number is also a natural numbers. So, it is going belongs to the n. So, addition is well defined. So, I can say that this binary operation is well defined. Second one is I am going to discuss the associativity. So, associative means I have x star y star z, and that is going to be x plus y plus z. So, this is true for all natural numbers, and then this is true for all x, y, z. So, belongs to the n. So, it is associative, that we have already discussed. Now, the main thing is that I will going to start with the third one. Now, we have to choose the element E such that if I take E plus x, then I should get x, and that should be equal to x plus E. So, in the natural numbers I have to have one number E such that this is satisfied. Now, my natural numbers, I know that the natural numbers are starting from 1, 2, 3, 4, 5 and so on. So, in this case suppose I take 2, then what should be the E so that I get 2? So, obviously that in this case my E should be 0, but that does not belongs to natural number n. So, this property is not satisfied. So, from here I can say that n is not a group under addition. So, this is not a group under addition. Then I take another example. So, instead of natural number, suppose I start with set of integers. So, we represent by z. So, in this case I will take that let the star binary operation, we choose addition by plus sign. Now, we know that the sum of two integer is integer. So, this is well defined. So, operation is binary operation is well defined. Now, I will start satisfying the properties. So, G1 is associative. So, now we know that the sum of any three integers, that is going to satisfy the associativity, because x star y star z, that is same as this one for all integer x, y, z belongs to z. So, this z is like this one. So, that is a capital Z, and this I can take as a small z. So, this one we just choose the, or I can just take this z. So, it is associative. Now, G2. So, I need a element E such that E plus x is going to be x plus E is going to be x, and this should be true for all x belongs to the set. So, whatever the set we are going to have. So, now in this case I know that if we take E is to be 0. So, in this case if E is to be 0, then I know that 0 plus any integer, it is going to be x, and this is true for all x belongs to integer. So, from here I can say that my E is 0, and that is we call it additive identity. So, this is a additive identity, and we know that this is unique in this case, because no any other elements we can find from the set of integer such that we add to x and we get this value of x other than 0. So, in this case it is unique. Then G3. So, in this case for any integer, suppose I take x that belongs to z, I need a element a such that if I put a plus x, that or x plus a, that should be equal to E, and E in this case it is 0. So, from here I mean that I need the additive inverse of the element x such that if I add to that one I get the value 0. So, from here I can say that a can be written as minus x, because I know that if it is 5, then minus 5 it is going to be 0. So, in this case my a is, I can choose minus of x, whatever the element is there I just choose the minus of that one and I will get the value 0. And from here I can say that a is an so this is a is my a is an additive inverse, and it is unique. So, from here, because I know that the inverse of 5 is always minus 5 and no any other integer is there which gives the value 0. So, it is also unique. So, from here I can say that this is a group. Now, I will satisfy the fourth property, and from here I know that x plus y can be written as y plus x. This is true for all x y belongs to the set of integers. So, in this case I can say that this group is this set is this binary operation is commutative, and from here I can say that set of integers is an abelian group, or we can say that Z is a commutative group. So, this way we can say that set of integer is a group, abelian group. Similarly, we can discuss another examples. For example, I can choose set of rationals or R the set of real numbers. So, in this case I can define the set of rational or the real numbers under different type of binary operation, and then we can check that whether it is going to be a group or not. So, that we will discuss in the next lecture. So, we stop here. So, today we have started with the course, and in that we just define the basics about that what is the binary operation and how the binary operation can be commutative or associative, and then we discuss the another definition, that is groups. So, in the next lecture we will continue with this one. So, thanks for watching. Thanks very much.